Have you ever looked up at the night sky and felt a sudden, overwhelming sense of mystery? That tug in your gut that makes you wonder, what if there's more to all of this than what we've been told? What if the stars above aren't just distant suns, but something far stranger, pixels in a cosmic display, glitches in an impossibly vast simulation? It sounds like science fiction, but what if it isn't? What if we're beginning to see the first signs of something truly mind-bending, the slow, silent breakdown of reality itself? That's exactly what we're exploring today. We're diving into one of the most captivating and controversial ideas in modern cosmology, the theory of galactic shells. Picture, if you will, layers upon layers of reality, like nested Russian dolls, each one containing its own rules, its own physics, its own version of existence. And now, imagine those layers beginning to fray at the edges. Scientists and theorists are uncovering cosmic anomalies, strange signals, unexplained gravitational ripples, patterns in the cosmic microwave background that shouldn't be there, clues that suggest our universe might not be the solid, stable reality we assume it is. Instead, it might be something closer to a projection, a carefully constructed illusion that's starting to show its seams. This isn't just a wild thought experiment. It's a journey into the deepest questions we can ask as conscious beings. If even a fraction of this theory holds weight, it could rewrite everything, not just our understanding of physics or astronomy, but the very nature of existence, consciousness, and our place in the cosmos. And you're coming along for the ride. In this video, we'll unravel the evidence, explore the science and the speculation, and venture into a possibility so profound it might just change how you see reality forever. So lean in, open your mind, and let's begin. To grasp this mind-bending concept, let's start with something familiar. Think about an onion with its many concentric layers. You can peel one back only to find another beneath it, each one separate yet part of the whole. Galactic shells are a bit like that, but on a cosmic scale. They are the theoretical layers, the fundamental boundaries and structures that might make up our reality if it is, in fact, a simulation. Imagine these shells not as physical objects you could touch, but as the very architecture of existence itself. The rules, the physics, the code that defines how everything operates, from the smallest subatomic particle to the largest galaxy cluster. If our universe is a simulation, it would need a framework to run on, a kind of cosmic operating system. Galactic shells could be the foundational layers of that system. The outermost shell might represent the most basic, underlying code, the laws of physics and mathematics that are immutable and constant. Then, within that, another shell could govern the rules for complex systems like gravity, light, and time. As we move inward through layer after layer, we might find shells that handle more specific operations like the formation of stars, the evolution of life, or even the emergence of consciousness itself. Each layer would be a distinct set of instructions, working in perfect harmony with the others to create the seamless, consistent reality we experience every day. This is strikingly similar to how complex computer programs and video games are built today. A modern video game, for instance, doesn't run on a single, monolithic block of code. It has layers. There's a core engine layer that handles the most basic calculations, things like rendering graphics and processing physics. Then, on top of that, another layer might manage the game's artificial intelligence, dictating how non-player characters behave. Another layer could control the user interface, what you see and interact with on the screen. Each of these layers is dependent on the ones below it, yet they function together to create an immersive, believable world for the player. Galactic shells propose that our universe might be built on a vastly more sophisticated version of this very same layered principle. The reason this idea is so compelling to physicists and philosophers is that it offers a potential explanation for some of the deepest mysteries in science. For example, why do the fundamental constants of the universe, the speed of light, the strength of gravity, have the exact, precise values that allow for life to exist. If our reality is constructed within these shells, those values wouldn't be random accidents of nature. They could be set parameters, lines of code written into the outermost, most fundamental layer of the simulation. They are the fixed rules of the game. Any change to that base code, even a tiny one, and the entire structure of reality as we know it would simply cease to function. This architectural view turns the universe from a chaotic accident into a meticulously engineered construct, with each galactic shell acting as a critical load-bearing wall in the cathedral of existence. But before we can truly appreciate the staggering implications of galactic shells, we need to understand the bedrock upon which this entire idea is built. This foundation is known as the simulation hypothesis, a concept that has gracefully leaped from the pages of philosophy into the halls of serious scientific debate. The modern conversation really began with a groundbreaking paper published in 2003 by the philosopher Nick Bostrom. His argument wasn't based on wild speculation, but on a cold, logical progression of thought. He proposed that at least one of three possibilities must be true. Either virtually all civilizations at our level of technological development go extinct before achieving advanced simulation capabilities, or almost no advanced civilizations have any interest in running simulations of their ancestors, or we are almost certainly living inside a simulation right now. The power of this trilemma is its simplicity. If we assume that humanity, or any other intelligent species, survives its technological adolescence and doesn't wipe itself out, and if we further assume that this advanced civilization would have even a modest curiosity about its own history or the nature of consciousness, then it stands to reason they would possess the computing power to create incredibly detailed ancestor simulations. They might run not just one, but billions of them. If that's the case, the number of simulated minds would vastly outnumber the one original biological civilization. Therefore, statistically speaking, the odds are overwhelmingly high that you and I are among the simulated ones, not the original biological beings. It's a statistical argument that is incredibly difficult to refute on its own terms. This philosophical starting point has gathered some astonishingly credible support from the world of hard science. Prominent astrophysicist Neil deGrasse Tyson has publicly stated that he finds the odds that we are living in a base reality to be very low, perhaps even 50-50. The iconic technologist Elon Musk has famously argued the odds are billions to one that we are not in a simulation, pointing to the exponential advancement of video game technology and virtual reality as a precursor to what a truly advanced civilization could achieve. This isn't just science fiction chatter. It's a premise that is being taken seriously by some of the sharpest minds of our time because it provides a potential framework to answer questions that traditional physics has struggled with. And that's where the concept of galactic shells becomes such a powerful and natural extension of this theory. If we accept the simulation hypothesis as a plausible or even probable model of our existence, we must then ask the next logical question: how would such a simulation actually be built and maintained? It wouldn't be a simple, flat program. Any sophisticated system, especially one of this unimaginable complexity, requires architecture. It needs layers of abstraction, a hierarchy of processes where the most fundamental rules are distinct from the higher-level phenomena they create. This layered architecture is precisely what the galactic shells theory describes. It moves the conversation from the philosophical if to the practical how, offering a structural model for how a simulated reality might actually operate, from its immutable base code to the dynamic, interactive experience of conscious life within it. So if the galactic shells model gives us a theoretical framework for how a simulation might be structured, the next step is to go looking for the evidence, the digital fingerprints, the cosmic lines of code that might have been left behind. And perhaps the most compelling place to start that search is with the oldest light in the universe, the cosmic microwave background, or CMB. This faint, cold glow is the remnant heat from the Big Bang, a snapshot of the infant universe when it was just 380,000 years old. For cosmologists, it's the closest thing we have to a foundation layer of reality, a fossilized imprint of the universe's initial conditions. And within this ancient light, scientists are finding anomalies, bizarre, unexplainable patterns that defy our standard models of physics. These aren't just minor statistical quirks, they are profound oddities that some researchers believe could be the first observable signs of our simulated reality's underlying architecture. One of the most persistent and controversial of these anomalies is known rather dramatically as the axis of evil. When the Planck satellite mapped the CMB in exquisite detail, it revealed that the temperature fluctuations across the sky aren't entirely random. Instead, they appear to be aligned along a specific plane, a particular direction in space. This is a huge problem. The standard cosmological model is built on the principle of isotropy, the idea that the universe on a large scale should look the same in every direction. There shouldn't be a preferred axis, a cosmic North Star for the entire fabric of reality. It would be like finding that all the continents on Earth subtly pointed toward one specific location in the sky. It suggests a fundamental bias, a tilt in the very foundations of the cosmos that simply shouldn't be there if the universe were a naturally evolved random system. Now consider this through the lens of the simulation hypothesis and the galactic shells model. In a complex computer simulation, especially one running on a substrate with physical limits, you might expect to find artifacts of the system's architecture. A preferred axis could be a telltale sign of the simulation's coordinate system, a kind of universal grid line that became faintly imprinted on the projected reality. It might be a relic of the processing constraints of the simulator itself. Perhaps the way data is stored or rendered creates a subtle directional bias. In essence, the axis of evil might not be an evil axis at all, but a structural marker, a seam between two galactic shells where the underlying code of the simulation becomes ever so slightly visible. Beyond this mysterious alignment, there are other, even stranger features. The CMB also contains what are known as cold spots, a vast, inexplicably cold regions that are far larger and much colder than our models can account for. One particular cold spot in the constellation Eridanus is so massive and so anomalous that it has defied all conventional explanations, from a gigantic supervoid to exotic physics. But what if these aren't physical structures in the classical sense? What if they are something else entirely? Within the galactic shells framework, a cold spot could be interpreted as a rendering error, a glitch in the matrix. It might represent a region where the simulation's processing load is exceptionally high, causing a drop in the fidelity of the projected reality. Alternatively, it could be a boundary zone, a transitional area between two different layers or resolutions within the nested shells of the simulation, where the rules of physics are interpreted slightly differently, resulting in an observable dip in energy. The most compelling part of this argument is that these anomalies persist. They have survived increasingly precise observations. Every time a new, more powerful telescope takes a look, these strange features are still there, stubbornly refusing to be explained away as mere instrumental noise or statistical flukes. For those who entertain the simulation hypothesis, this is exactly what we should expect to find. A perfect, flawless simulation would leave no trace of itself. It would be completely self-contained and consistent. But a simulation running on a finite computer, even an unimaginably powerful one, would have limits. It would eventually show signs of compression, of data constraints, or of the underlying mathematical architecture it's built upon. The CMB anomalies are the universe's equivalent of finding a pixelated texture in a video game when you zoom in too far, or noticing a repeating pattern in a computer-generated landscape, tiny clues that point to a constructed reality. While the cosmic microwave background offers a glimpse into the universe's largest scales, some of the most convincing evidence for a layered reality might actually be found in the bizarre behavior of the very smallest things we know, quantum particles. This is the strange and spooky world of quantum entanglement, a phenomenon so counterintuitive that even Albert Einstein famously dismissed it as spooky action at a distance. At its heart, entanglement describes a powerful connection between two particles, like a pair of electrons or photons that have interacted and become linked. Once entangled, these particles form a single, unified quantum system. Here's where it gets truly weird. If you then separate them by any distance across a lab, a continent, or even light years of empty space, measuring the property of one particle, like its spin or polarization, will instantly force its distant partner to assume a corresponding state. This connection appears to happen faster than the speed of light, a direct violation of the cosmic speed limit set by Einstein's theory of relativity, which states that no information or influence can travel faster than light. From a classical physics perspective, this makes absolutely no sense. It suggests an influence jumping between 2 points with zero travel time, a paradox that has baffled scientists for nearly a century. But through the lens of the Galactic Shells model, this spooky action might not be so spooky after all. Instead, it could be a glaring clue pointing to the underlying programming of our reality. In a complex simulation, information doesn't need to travel in the way we think of it. Two entangled particles might not be two separate entities sending a signal to each other. They could be two expressions of a single, underlying variable in the simulation's code. Their connection isn't maintained by some unknown force flying through space. It's maintained because at the most fundamental processing layer, they are never truly separated to begin with. They share a common origin point in the program's data structure. When you measure one, you're simply updating that shared variable, and the change is reflected everywhere that variable is referenced instantly, because it all happens within the same processing cycle of the simulator. This would explain the instantaneous link without breaking any rules, because no information is actually moving. It's just a single piece of data being accessed and updated. This interpretation transforms entanglement from a physics problem into a potential software feature. The phenomenon could be a direct manifestation of the simulation's optimization protocols. Rendering a universe of uncountable particles, each with its own independent state, would be an astronomically inefficient processing task. It would demand unimaginable computational resources. But if the simulation is built with layers of abstraction, it could use a kind of data compression. Entangled particles might be a brilliant shortcut, a way for the program to handle groups of related objects not as billions of individual entities, but as linked clusters defined by a smaller set of shared properties. This drastically reduces the processing load. The strange, probabilistic nature of quantum mechanics, where particles exist in a haze of potential states until observed, fits perfectly with this idea. It mirrors how a video game engine doesn't render every detail of a vast open world at once. It only loads the high-resolution textures and defines the precise properties of objects when a player is looking directly at them. The rest of the world exists in a lower resolution, probabilistic state until it's needed. In our universe, the act of measurement, of observation, might be the trigger that forces the simulation to render a definite state, collapsing all the possibilities into a single, concrete outcome. The most compelling evidence for this view might be found in the growing success of quantum computing. These extraordinary machines don't work like classical computers. They leverage the principles of superposition and entanglement to perform calculations. And remarkably, they operate in a way that looks less like traditional physics and more like programming. A quantum computer essentially asks the universe to solve a problem by exploring all possible answers simultaneously within a quantum state, and then uses interference, a wave-like property, to cancel out the wrong answers and amplify the correct one. For many scientists, this is less like harnessing a natural force and more like directly interacting with the operating system of reality. It's as if we've discovered a way to write code that runs on the hardware of the galactic shells themselves. The fact that we can engineer devices that utilize these quantum rules so effectively suggests that these rules are consistent, reliable, and programmable. The hallmarks of a well-designed system, not the chaotic outcomes of random chance. So, if quantum entanglement acts as a window into the simulation source code, then the boundaries between the theoretical galactic shells might be where this code is most active and visible. The instantaneous connection between particles could be a phenomenon that occurs when information passes between two layers of the simulation without being processed through the slower, rules-based physics of the intermediate layers. It's a direct data transfer bypassing the usual rendering pipeline. This would make the quantum realm not just another layer of reality, but perhaps the fundamental substrate, the deepest operational layer where the actual computations of the universe are performed. The larger, classical world we experience with its definite objects and strict causality would then be the user interface, a high-level projection built upon this buzzing, probabilistic quantum engine. The anomalies we detect, from the axis of evil in the CMB to the spooky links between particles, become understandable not as errors, but as features inevitable glimpses of the immense and layered architecture that sustains everything we know. This leads us to one of the greatest and most persistent mysteries in all of modern cosmology, the enigma of dark matter and dark energy. For decades, scientists have known that the universe we can see, the stars, galaxies, planets, and everything they're made of accounts for a pitifully small 5% of the total mass and energy in the cosmos. The other 95% is completely invisible, undetectable by any telescope or instrument we have, yet its gravitational effects are undeniable. Dark matter provides the extra glue that holds spinning galaxies together, preventing them from flying apart. Dark energy is the mysterious force causing the expansion of the entire universe to accelerate at an ever-increasing rate. They are the dominant forces shaping cosmic evolution, and we have absolutely no idea what they actually are. But what if this isn't a failure of our science, but rather a profound clue about the nature of reality itself? Within the galactic shells model, dark matter and energy might not be physical substances at all. Instead, they could be the observable signatures of the simulation's underlying architecture, the processing power and framework required to render and maintain the reality we experience. Think of it like the back-end processes of a massively complex video game. When you play, you see the rich graphics, the characters, the physics of the world. What you don't see is the enormous amount of computational work happening behind the scenes. The graphics engine rendering the environment, the physics engine calculating collisions, the artificial intelligence managing non-player characters, and the memory allocation keeping everything running smoothly. This hidden processing consumes the vast majority of the computer's resources, yet it remains completely invisible to the player within the game. Now, scale that idea up to a cosmic level. The 5% of the universe we can see and interact with the ordinary matter would be the rendered output, the beautiful graphics of the simulation. The 95% represented by dark matter and dark energy could be the universe's equivalent of that hidden computational load. Dark matter's gravitational effects might be the manifestation of the simulation's data structures, the invisible scaffolding and framework that defines where galaxies should form and how they should hold their shape. It doesn't interact with light because it's not part of the rendered world. It's part of the underlying code that organizes it. Dark energy presents an even more fascinating possibility. The accelerating expansion of the universe is one of the most bizarre observations in physics. Why is the fabric of space-time itself stretching faster and faster? In the simulation hypothesis, this could be interpreted as a form of computational inflation. As the simulation runs, the amount of data it must process, the history of every particle, the state of every star is constantly increasing. To prevent a catastrophic system overload or a slowdown in processing, the simulator might need to allocate more and more memory or processing resources to the task of maintaining the reality. The observable effect of this resource allocation from our perspective inside the simulation could be the relentless, accelerating expansion of space itself. Dark energy wouldn't be a force in the traditional sense, but a readout of the ever-growing computational power being devoted to keeping the simulation operational and consistent across its vast, layered shells. This perspective elegantly solves several thorny problems at once. It explains why these two components are so dominant yet completely undetectable by conventional means. We're not meant to interact with the framework of the program, only with the reality it projects. It also provides a reason for their seemingly fine-tuned values. The ratios of dark matter to dark energy to ordinary matter aren't arbitrary cosmic constants. They could be the optimal settings for a stable, long-running simulation. Too much processing power allocated to rendering visible matter, and the simulation might become unstable or too resource-intensive. Too little, and the reality would lack the complexity needed for stars, planets, and life to emerge. The precise balance we observe could be the hallmark of an incredibly sophisticated and efficient engineering project, one that has been running smoothly for nearly 14 billion years. The mysteries of dark matter and dark energy, which have stubbornly resisted explanation through purely physical models, might finally make sense when viewed not as physics problems, but as the inevitable artifacts of a reality built upon a deeper, layered digital foundation. This architectural view of the universe as a meticulously engineered construct, with dark matter and dark energy as its fundamental processing framework, leads us to one of the most haunting questions in all of science. If the cosmos is so perfectly set up for life, and if intelligent civilization should be common, then where is everybody? This is the famous Fermi Paradox, a question that has puzzled astronomers for decades. The sheer scale and age of the universe suggest it should be teeming with intelligent life, yet we see no signs of it, no signals, no visitations, no grand cosmic engineering projects. Countless solutions have been proposed, from the dark idea of a great filter that wipes out civilizations before they can expand, to the possibility that we are simply the first. But what if the answer is far stranger and intimately connected to the galactic shells we've been exploring? What if advanced civilizations don't vanish because they die out, but because they graduate? They might discover the true nature of their reality and find a way to exit the simulation itself. Imagine a civilization that reaches a technological singularity, a point where its intelligence and understanding accelerate beyond our comprehension. Such a culture wouldn't just be asking questions about physics and biology, it would be probing the fundamental nature of existence. They would likely detect the same anomalies we are beginning to see, the strange alignments in the cosmic microwave background, the spooky action of quantum entanglement, the inexplicable dominance of dark energy. For them, these wouldn't be mere mysteries, they would be clues, a breadcrumb trail left by the architects of the simulation. Their most powerful telescopes and particle colliders might not be pointed outward at the stars, but inward at the source code of reality itself. Their ultimate mission would shift from cosmic exploration to cosmic hacking, attempting to reverse engineer the simulation and understand its rules from the inside. The concept of a great filter takes on a completely new meaning in this context. The filter might not be an external catastrophe like an asteroid impact or a self-inflicted nuclear war. It could be an internal, intellectual threshold the moment a civilization gains enough knowledge to perceive the boundaries of its own reality. Once that line is crossed, their entire focus would change. Why would a species invest immense resources in building interstellar arcs or sending generation ships across the void if they suspected the void itself was a projection? Their energy would be directed toward manipulating the layers of the simulation, perhaps even communicating with or appealing to the creators beyond the outermost galactic shell. The silence we hear across the cosmos might not be a silence of absence, but a silence of intense, focused activity on a plane of existence we cannot yet perceive. This idea provides a startlingly elegant resolution to the Fermi Paradox. The reason we don't see advanced civilizations colonizing the galaxy is because they have moved on to a higher level of reality. They haven't left behind ruins or relics because their greatest achievements weren't physical. They were metaphysical. Their departure might be as subtle as a data transfer, leaving their star systems pristine and quiet. From our perspective, it would look as if they simply vanished, their planets becoming silent tombs. But in truth, they could have transcended, exiting the simulation in a way that leaves no trace for those still operating within its rules. This transforms the universe from a lonely place into something resembling a grand tutorial level, a training ground where consciousness is forged and tested until it is ready to move onto the real world beyond the simulation. This isn't just philosophical speculation. It reframes our entire search for extraterrestrial intelligence, or SETI. For decades, we've been listening for radio waves and looking for optical signals, operating on the assumption that other civilizations would communicate through channels we understand. But if other species have already advanced to manipulating the simulation source code, their methods of communication would be utterly alien to us. They might not use electromagnetic waves at all. Instead, they could be sending messages by subtly altering the constants of physics in their local region of space, or creating intentional, patterned glitches in the quantum foam. Their messages might be hidden in plain sight, encoded in the very anomalies that we dismiss as cosmic errors. The axis of evil in the CMB might not be an accident. It could be a signature, a graffitied tag on the fabric of reality, left by a civilization that learned to rewrite its own rules. Ultimately, this perspective offers a profound and strangely hopeful vision for humanity's future. The great silence of the universe is not a cause for despair, but a challenge and an invitation. It suggests that the pinnacle of intelligence is not galactic domination, but cosmic understanding. The goal is not to cover the galaxy in a blanket of cities, but to uncover the truth of our existence. If other civilizations have successfully made this leap, it means it is possible. The same clues are available to us: the cold spots, the entangled particles, the dark energy. These are not just puzzles for physicists. They are the first pages of a manual left behind for us, a guide on how to navigate the layers of the galactic shells. Our journey as a species may just be beginning, and our ultimate destiny might not be among the stars but beyond them, in the reality that lies outside the simulation. But if the great silence of space hints at civilizations that have transcended our plane of existence, then the most profound clues about how they might have done it could be lurking in the most destructive places in the universe: black holes. These cosmic monsters are famous for their immense gravity, so powerful that not even light can escape their grip. But beyond their terrifying reputation, black holes present physicists with a paradox so fundamental that it threatens to unravel our very understanding of reality. This is known as the black hole information paradox, and it might just be the ultimate key to understanding the layered architecture of a simulated cosmos. The problem begins with a simple, unsettling fact. According to Einstein's theory of general relativity, when something falls into a black hole, it is gone forever. Its mass, energy, and charge are added to the black hole, but all of the specific details about that object, the unique arrangement of atoms that made up a star, the precise genetic code of a hypothetical astronaut, every bit of information that defined it seemed to be irretrievably lost behind the event horizon. This creates a direct conflict with a cornerstone principle of quantum mechanics, the law of information conservation. In the quantum world, information cannot be created or destroyed, it can only be transformed. The universe at its heart is supposed to be predictable. If you could know the exact state of every particle, you could theoretically rewind time and see how everything came to be. But if black holes truly destroy information, then the universe has a giant, irreversible eraser. This isn't just a minor inconsistency, it's a glaring contradiction between the two most successful theories in physics, suggesting that our fundamental picture of how reality works is deeply flawed. Now, let's view this same paradox through the lens of our galactic shells model. What if the information isn't being destroyed at all? What if a black hole isn't a cosmic shredder, but a cosmic processor, a transfer point or a data compression unit operating between the layers of the simulation? Imagine a sophisticated computer system managing a vast virtual world. To keep the simulation running efficiently, it can't store every single bit of data forever. The history of every particle, every interaction over billions of years, would represent an unimaginable accumulation of information. The system would need a way to manage this data, to process it, compress it, or perhaps even archive it. A black hole could be the physical manifestation of that essential housekeeping function. When an object crosses the event horizon from our perspective within the simulation, it appears to vanish. But its information might not be deleted. Instead, it could be translated. It might be processed from the complex, rendered state of our observable universe, the top-level shell, into a more fundamental, compressed format in a deeper layer of code. The two-dimensional information that is theorized to be encoded on the event horizon itself, a concept known as the holographic principle, could be the data waiting to be processed. The black hole's subsequent evaporation through Hawking radiation, which seemingly releases only random thermal energy, might not be a destruction of information, but its final transmission or storage in a different, more efficient form within the simulation's architecture. The paradox vanishes because the information isn't lost, it's simply moved to a part of the system we cannot access. This transforms black holes from terrifying endpoints into potential gateways or even routers in the cosmic network. Their incredible density and gravity could be a side effect of an immense concentration of processing power, a localized region where the computational workload of simulating that portion of spacetime is exceptionally high. The event horizon would then be the boundary between two different resolutions or two different layers of the simulation, the point where the detailed, classical laws of physics we experience give way to the raw, probabilistic quantum code that underpins them. The mysterious singularity at a black hole's heart might not be a point of infinite density, but a symbolic representation of a data output or input node, a place where information is exchanged between galactic shells. This perspective offers a breathtakingly elegant solution to the information paradox that has stumped physicists for decades. The information is conserved because the simulation, like any well-designed program, must conserve its state data to remain consistent and stable. It doesn't break its own rules, it just operates on a level of reality we are only beginning to glimpse. The strange, counterintuitive laws that govern black holes start to make a new kind of sense when we stop thinking of them as purely astronomical objects and start considering them as active components in a cosmic computational engine, vital to maintaining the integrity and continuity of the simulated reality we call home. Yet for all their destructive mystery, black holes might not be the most direct evidence of a layered reality we can observe. That title could belong to something far larger and even more inexplicable, a colossal, invisible force dragging our entire galactic neighborhood through the cosmos. This is the mystery of the Great Attractor, a gravitational anomaly of such immense power that it challenges our very understanding of the universe's structure and could point directly to a glitch in the matrix itself. Located in the direction of the constellations Centaurus and Hydra, roughly 250 million light-years away, lies a point in space that exerts a gravitational pull so formidable it is drawing our own Milky Way galaxy, along with thousands of others, toward it at a staggering velocity of over 14 million miles per hour. We cannot see what is pulling us. Our view of this region is completely obscured by the dense band of stars, gas, and dust at the center of our own galaxy, the so-called zone of avoidance. It's as if we are being pulled toward a cosmic stage hidden behind a thick, impenetrable curtain. Early observations revealed this motion was far too great to be explained by the visible mass in that direction, leading scientists to label the source of this pull the Great Attractor. It behaves like a gigantic gravitational anchor in the void, and its existence suggests there is either an enormous amount of mass we cannot see, or our understanding of gravity on the largest scales is fundamentally incomplete. From the perspective of classical cosmology, the prevailing explanation involves dark matter. The Great Attractor is often described as the core of the Laniakea supercluster, an immense filament of galaxies of which we are a part. In this view, the gravitational pull is caused by a concentration of dark matter so vast that it dominates the motion of all nearby galaxies. This is a reasonable assumption within the Standard Model, but it still feels like a placeholder, an appeal to the unknown 95% of the universe to explain another cosmic oddity. However, when we apply the Galactic Shells model, a far more intriguing possibility emerges. What if the Great Attractor isn't a concentration of dark matter, but a structural feature of the simulation itself? It could represent a point where the rendering rules of our reality are breaking down, or where two layers of the simulation are interacting in an unexpected way. Consider the architecture of a vast, simulated universe. To run efficiently, it would likely be divided into sectors or domains, each managed by its own set of processes within the larger computational framework. The boundaries between these sectors might not be perfectly seamless. The Great Attractor could be such a boundary, a place where the data structure of one galactic shell interfaces with another. The immense gravitational pull we detect might not be gravity in the traditional sense, but a kind of data drift or processing bias. It could be the observable effect of a differential in the simulation's computational load between two regions, a subtle tug caused by the underlying system allocating more resources or applying slightly different physical rules in one sector compared to another. In essence, we wouldn't be falling toward a mass, we'd be experiencing a cosmic current flowing toward a node in the processing network. This interpretation transforms the anomaly from a cosmological puzzle into a potential design feature or even a flaw. In complex software, especially in distributed systems, you can sometimes encounter issues where one server or node develops a slight processing lag or a different internal state compared to others. The system works to correct this, creating a kind of pull as data synchronizes. The Great Attractor could be the universe's version of this, a point where the simulation is working to maintain consistency across its layered shells, and that effort manifests as a mysterious directional force on the reality within it. The fact that it lies in a region obscured by our own galaxy's core could be more than mere coincidence. It might be a deliberate design element, placing this architectural seam in a location where its true nature is hardest for its inhabitants to observe directly. The most compelling evidence for this view may come from the sheer scale of the motion involved. The pull of the Great Attractor is just one part of an even larger and more mysterious flow. Our entire local volume of space, including the Great Attractor itself, is also being pulled toward something infinitely more massive and distant known as the Shapley Attractor. This suggests we are witnessing not just one anomaly, but a hierarchy of them, a cascade of gravitational influences that could map directly onto the layered data structure of a simulation. Each attractor might correspond to a different level of processing jurisdiction within the galactic shells, with the largest flows pointing toward the most fundamental, base layer nodes of the entire system. We are not just looking at hidden masses, we could be looking at the invisible architecture of reality itself, revealed only by the subtle motions it imposes on the galaxies within it. This perspective doesn't just solve a mystery, it redefines our entire approach to cosmology. The goal shifts from mapping the distribution of dark matter to reverse engineering the source code of the universe. The Great Attractor becomes a celestial signpost pointing not toward a hidden cluster of galaxies, but toward a deeper truth about the constructed nature of our existence. It is a gravitational glitch, a profound anomaly that whispers of the layers beyond our own, urging us to look past the veil of visible matter and question the very fabric of the reality we take for granted. But perhaps the most precise and perplexing challenge to our understanding of cosmic architecture comes not from the shadows of dark matter or the pull of invisible attractors, but from our most careful attempts to measure the universe's most fundamental behavior, its expansion. This is the Hubble tension, a growing and seemingly irreconcilable discrepancy that strikes at the very heart of cosmology. For over a century, we've known the universe is expanding, with galaxies rushing away from each other as space itself stretches. The rate of this expansion is called the Hubble constant, a single number that should be a cornerstone of our cosmic model. Yet, when scientists measure this number using two different, highly trusted methods, they get two different answers. It's as if two of the most accurate clocks ever built, designed to keep perfect time, are stubbornly ticking at different speeds, and no one can figure out why. One method relies on the local, modern universe. Astronomers use pulsating stars called Cepheid variables and cataclysmic stellar explosions known as Type 1a supernova as standard candles. Because their intrinsic brightness is known, measuring how dim they appear tells us their distance, while their redshift tells us how fast they are moving away. This builds a cosmic distance ladder, rung by rung, giving us a precise measurement of the expansion rate today. The other method looks back to the universe's infancy. By analyzing the intricate patterns in the cosmic microwave background, the afterglow of the Big Bang, scientists can use the well-established laws of physics to predict how that expansion should have evolved over time, leading to a specific value for the present-day expansion rate. Both methods are exquisitely precise, but they disagree by a small yet significant margin. The local measurement suggests a faster expansion rate, while the early universe measurement predicts a slower one. This isn't a large error bar, it's a persistent, stubborn gap that has only widened with more precise data, suggesting a fundamental flaw in our model. Within the standard cosmological model, this tension is a crisis. It implies that our understanding of the universe's contents, its history, or the very laws of physics is incomplete. Perhaps there is a new, unknown particle or a strange property of dark energy at work. But what if the problem isn't with the physics, but with the platform on which that physics runs? The Galactic Shells model offers a radical but compelling explanation. The Hubble tension might be a rendering inconsistency. In a complex simulation spanning vast scales and epochs, it's possible that the rules are not applied with perfect uniformity across all layers or all regions. The method using the local universe measures expansion by observing stars and galaxies within our own cosmic neighborhood, our local shell layer. The method using the CMB, however, is essentially reading the initial conditions from the deepest, most fundamental base layer of the simulation. A discrepancy between the two could indicate that the simulation's rendering engine applies a slightly different set of parameters or processing rules to the present day, high-detail local environment compared to the underlying base code from which it was launched. The local measurement might be influenced by the specific data compression or processing shortcuts used to render our contemporary, complex universe of galaxies, while the CMB measurement is reading the pristine, unadulterated initial settings. This wouldn't be a bug so much as a necessary feature for efficiency, but it would create a measurable inconsistency from the perspective of an observer within the simulation. It would be like a video game where the physics for a pre-rendered cinematic cutscene calculated in advance doesn't perfectly match the physics of the real-time game engine you interact with. Both are valid within their own context, but they are processed differently, leading to a slight mismatch. This interpretation transforms the Hubble tension from a troubling paradox into a potential signature of the simulation's architecture. The fact that the two methods, one looking at the source code of the early universe and one measuring the rendered output of the modern universe, disagree, could be the most direct evidence yet that we are living within a constructed reality with multiple, slightly inconsistent layers. The tension is the seam showing. It suggests that the galactic shells are not perfectly synchronized, that the translation of the fundamental laws from the base code to the high-level experiential layer introduces a tiny but measurable drift. For those seeking evidence of a simulation, this isn't a problem to be solved. It's a clue to be followed, a whisper from the machine telling us that reality is not as monolithic as it appears. For decades, physicists have been engaged in a quest for what many consider the holy grail of modern science, a single, elegant theory that perfectly unites the two great pillars of 20th century physics. On one hand, we have quantum mechanics, which describes the bizarre, probabilistic world of the incredibly small with breathtaking accuracy. On the other, we have Einstein's general relativity, which masterfully depicts gravity as the curvature of spacetime itself, governing the motion of planets, stars, and galaxies. Individually, these theories are monumental achievements, each verified by countless experiments. Yet, when we try to merge them to describe a scenario where both are critically important, like the center of a black hole or the first moments of the Big Bang, the entire framework collapses into a mess of mathematical infinities and logical contradictions. They are fundamentally, stubbornly incompatible. From a classical perspective, this is the greatest unsolved problem in physics. But through the lens of our galactic shells model, this incompatibility might not be a problem at all. It could be the most glaring evidence that we are looking at two entirely different programming languages, two distinct rule sets governing separate layers of the simulation. Think of it like this. Imagine a vast, multi-layered video game developed by a massive team. The team handling the core engine might write their code in one specific programming language, optimized for raw processing power and rendering the fundamental laws of the world. This is the domain of general relativity, the smooth, continuous, geometric code that handles the large-scale structure of spacetime. It's elegant, deterministic, and it paints reality with a broad brush. Meanwhile, a different team, responsible for rendering the behavior of every tiny particle and force within that world, might use a completely different language, one built for handling probability, randomness, and discrete interactions. This is the quantum world, a realm of chance, entanglement, and wave functions. Both teams are brilliant, and both their codebases work flawlessly within their own designated domains. The problem arises at the boundaries where the two systems have to talk to each other. The data types don't match, the functions can't call each other correctly, and the entire program threatens to crash. That boundary, that interface where the quantum code meets the relativity code, is where we find the singularity of a black hole or the instant of the Big Bang. The incomprehensible nature of these extremes isn't a failure of our intellect. It could be a simple data-type mismatch in the cosmic source code. This interpretation resolves the conflict not by forcing a union, but by accepting a fundamental separation. The two theories cannot be unified because they were never meant to be one. They are the operational software for two different galactic shells. Quantum mechanics, with its probabilistic, information-centric rules, could be the programming language of the deepest, most fundamental processing layer, the level where the actual computations of the universe are performed. General relativity, with its smooth, geometric description of gravity, would then be the high-level language of the rendered reality, the user interface we experience. We are essentially trying to use the rules of the graphics engine to explain how the central processing unit works, and it's no surprise that the translation fails. The infamous difficulty of quantizing gravity, of describing the gravitational force in terms of discrete particles or quanta, might be because gravity isn't a force that emerges from the quantum layer at all. Instead, it could be a property of the rendered simulation, a geometric effect that arises from the way the simulation projects its data into an experiential, four-dimensional spacetime for its inhabitants. The fact that these two rule sets work perfectly within their own domains but fail catastrophically at their intersection is precisely what we would expect from a layered computational system. The moments where they are forced to interact like at a singularity are the moments where the simulation's architecture is stretched to its absolute limit, where the raw data of the quantum layer is being translated into the experiential reality of the relativistic layer. The mathematical infinities that appear are not signs that our math is wrong, but that we are hitting the limits of the simulation's resolution, the point where the rendering process breaks down because the two underlying systems were not designed for deep integration. They are glitches revealing the seams between the separate, magnificently complex shells that make our existence possible. This cosmic incompatibility, far from being a frustrating dead end, could be the most profound evidence yet that we are peering into the layered heart of a constructed reality. This brings us to one of the most mind-bending thought experiments in all of physics and philosophy, a paradox that questions the very nature of our consciousness and its place in the cosmos, the Boltzmann brain. To understand it, we need to travel back to the 19th century and the work of the physicist Ludwig Boltzmann. He was grappling with a concept called entropy, which is essentially a measure of disorder in a system. The second law of thermodynamics states that the total entropy of a closed system always increases over time. Things move from order to disorder. A cup of coffee cools down, a sandcastle washes away, a star burns out. But Boltzmann made a startling realization. In a universe that has existed for an almost infinite amount of time and is governed by random chance, even the most incredibly improbable events must eventually happen. Given enough time, all the atoms in a room could randomly bounce around and suddenly, spontaneously form a perfect, functioning pocket watch. It's astronomically unlikely, but in an infinite universe, it's not impossible. Now take that idea to its ultimate, terrifying conclusion. What is the most complex, ordered thing we know of? A human brain, complete with memories, thoughts, and a sense of self. In a vast, old, and random universe, it is statistically more likely for a single, fully formed, self-aware brain to spontaneously pop into existence from the chaos, complete with a full set of false memories of a life it never lived, than it is for an entire, ordered, 13.8 billion-year-old universe with galaxies, planets, and life to evolve naturally. You, sitting there watching this video, should far more likely be one of those random, disembodied Boltzmann brains, flickering into existence for just a moment with the illusion of a body and a world, than a real person in a real, stable cosmos. The fact that we observe a vast, coherent, and ancient universe, and not just fleeting moments of isolated consciousness, is a profound problem. It suggests that our standard model of cosmology is missing something crucial, something that strongly favors ordered structures over random fluctuations. This is where our Galactic Shells model offers a powerful and elegant resolution. The Boltzmann brain paradox only holds true if we assume the universe is a closed, random system slowly evolving toward maximum disorder. But if our reality is a constructed simulation built upon stable, layered shells of code, then its inherent order is not a statistical fluke, it's a design feature. The paradox vanishes because the universe isn't random, it's engineered. The galactic shells act as a protective, regulatory framework that actively maintains consistency and suppresses the kind of random fluctuations that would lead to Boltzmann brain. The laws of physics aren't passive suggestions. They are enforced rules, lines of code running on a deep processing layer that ensures reality remains coherent, predictable, and stable over colossal timescales. We don't see random brains popping into existence for the same reason we don't see random, glitched characters suddenly appearing in the middle of a carefully programmed video game. The system's architecture prevents it. However, this solution leads to a chilling and fascinating corollary. If the galactic shells are what maintain this perfect order, then the cosmic anomalies we've been exploring, from the axis of evil to the Hubble tension, could be interpreted as something far more significant than mere curiosities. They might be the first signs of system decay. After nearly 14 billion years of runtime, even the most perfectly engineered simulation could begin to experience wear. The processing load of maintaining such a complex reality might be causing microscopic errors to accumulate. The shells, those perfect layers of code, might be starting to degrade, their flawless enforcement of the rules beginning to waver ever so slightly. The glitches we're detecting are not proof against the simulation hypothesis. They could be the very evidence for it, showing us a reality that is no longer in its prime. A simulation that is, for the first time, starting to show its age. This perspective transforms our place in the cosmos. We are not unlikely observers in a random universe, but potentially timely witnesses to a truly cosmic event. We exist in a narrow window where the simulation is still stable enough to support complex life and conscious inquiry, but has become old enough that its underlying architecture is finally becoming visible to us. We are living in the era when the machine, for the first time, is beginning to whisper. The ordered reality we take for granted might not be a permanent state, but a temporary and perhaps fragile condition maintained by a system that is now, ever so slowly, breaking down. This doesn't mean reality will dissolve tomorrow, but it suggests that the seamless cosmic order that prevents Boltzmann brains is not invincible. It is a maintained state, and we may be the first generation to begin to perceive the immense layered machinery that has been holding it all together. This brings us to a mystery closer to home, a puzzle that emerged not from the depths of space but from within our own solar system, emanating from the humble probes we sent on their way to the stars. For decades, scientists were utterly baffled by the strange behavior of the Pioneer 10 and Pioneer 11 spacecraft. These twin explorers, launched in the early 1970s, were humanity's first missions to the outer planets and beyond. As they journeyed toward the edge of our solar system, navigators on Earth tracked their positions with incredible precision, but something was wrong. Both spacecraft were experiencing a tiny, unexplained, and constant acceleration back toward the Sun. This minuscule push, just about 10 billion times weaker than the gravity we feel on Earth's surface, was so small it was like adding a single grain of sand to the weight of the spacecraft each day. Yet, over years and years of travel, this tiny force added up, pulling the Pioneers off their predicted courses by hundreds of thousands of miles. It became known as the Pioneer Anomaly, and for nearly 30 years it resisted all conventional explanations. The scientific community exhausted every possible physical cause. Was it the gentle pressure of sunlight pushing back on the spacecraft? Careful calculations showed it wasn't nearly enough. Could it be the tiny amount of heat radiating from the probe's nuclear power sources, acting like a weak photon rocket? This was a leading theory for a while, but even after incredibly complex thermal modeling, a small, stubborn portion of the anomaly remained unaccounted for. Perhaps it was some unknown form of dark matter lurking in our solar system, or even a minor error in our understanding of gravity itself. One by one, each earthly explanation was proposed, tested, and ultimately found wanting. The Pioneer Anomaly became a classic, enduring enigma, a whisper from the void that something in our fundamental model of the solar system was ever so slightly incorrect. It was eventually resolved, or so the official story goes, by attributing it almost entirely to that anisotropic thermal radiation, the heat theory. but for many physicists that resolution never felt entirely satisfying. It was a close approximation, a best-fit answer, but it left a lingering sense that a deeper truth had been glossed over. What if that tiny, persistent tug wasn't a flaw in our engineering models, but a fleeting encounter with the architecture of reality itself? Imagine the Pioneer probes, having traveled for decades beyond the orbit of Pluto, venturing further from the Sun than any human-made object had ever gone before. In their quiet, lonely journey, they were the first to reach a region of space we had never directly probed. Now, consider the Galactic Shells model. If our reality is a layered construct, it's reasonable to assume that these layers aren't perfectly uniform all the way through. There could be boundary zones, transitional regions between one shell and the next where the rules, the constants, or the very rendering of physics experiences subtle shifts. The Pioneer spacecraft, in their immense journey, might have been the first human objects to brush up against one of these boundaries. From this perspective, the anomalous acceleration might not have been a force acting on the probe at all, but a slight change in the rules of the game within that boundary layer. Perhaps the gravitational constant g was minutely different in that region. A tiny increase in the value of g would make the Sun's gravitational pull seem slightly stronger from the probe's perspective, creating the precise illusion of an extra tug sunward. Alternatively, it could have been a subtle effect of the simulation's rendering process. As the probe moved into a less densely populated region of the simulation further from the major gravitational sources like the Sun and planets, the computational methods for calculating its trajectory might have shifted to a different, coarser algorithm, one that introduced a systematic bias into its motion. The anomaly wouldn't be a physical force, but a rounding error in the cosmos. The most compelling part of this idea is that the effect was so small and so constant. It wasn't a violent glitch or a sudden system crash. It was a gentle, persistent drift. This is exactly what you might expect from a transition between two vast, stable layers of a simulation, a seamless handoff that is almost but not quite perfect. The fact that the anomaly was later observed in the trajectories of other distant spacecraft, like the Galileo and Ulysses probes, adds further weight to the argument. This wasn't a unique problem with the Pioneers. It was an environmental effect, a feature of a specific region of space that multiple objects passed through. The official thermal explanation essentially patched over this cosmic oddity with a local, engineering-based answer, but it never truly addressed why the effect manifested so uniformly in such a specific deep space environment. The Pioneer anomaly, revisited through this lens, stops being a solved problem and transforms into a potential data point, a breadcrumb left by a spacecraft that briefly sailed along the seam between two galactic shells and reported back a whisper of the strange physics that exists there. Yet if the faint, persistent tug of the Pioneer anomaly hinted at a subtle warping of spatial rules at the edges of our solar system, an even more fundamental pillar of reality might be showing signs of strain, time itself. Einstein's theory of relativity gifted us with the stunning revelation that time is not a universal constant ticking away at the same rate for everyone. Instead, it's a fluid, malleable dimension stretched and compressed by gravity and velocity, a phenomenon we call time dilation. A clock in a powerful gravitational field, like that near a black hole, ticks far slower than a clock in the empty void of intergalactic space. An astronaut traveling at a significant fraction of the speed of light would age less than their twin who remained on Earth. This isn't science fiction. It's a proven, everyday reality for the ultra-precise atomic clocks aboard GPS satellites, which must have their timers constantly corrected for these relativistic effects to keep our navigation systems accurate. For over a century, this beautiful, if counterintuitive, aspect of physics has been one of the most rigorously tested and confirmed principles in all of science. But what if the universe's clock is starting to tick inconsistently? Astronomers are now scrutinizing some of the most distant and violent events in the cosmos: supernova explosions and gamma-ray bursts, to measure the stretching of time across vast cosmological distances. The principle is straightforward. We know the intrinsic properties of these brilliant stellar cataclysms. We understand the precise physics of how they brighten and fade. By observing these events in galaxies billions of light years away, we can measure how the expansion of the universe has stretched the light during its long journey to us. This stretching, called cosmological redshift, affects not just the color of the light but the very passage of time as we observe it. The flickering and fading of the distant explosion should appear to happen in slow motion compared to a nearby equivalent event. This time dilation effect is a critical prediction of our standard model of cosmology, and for the most part it holds true. However, a growing number of puzzling observations are revealing small but persistent anomalies in these measurements, suggesting that time might not be dilating in quite the way our models predict. Some studies of these far-off supernovae have reported that the observed time dilation effect appears to be slightly weaker than expected. The distant explosions don't seem to be playing out in quite as much slow motion as the theory says they should. The discrepancy is subtle, often buried in the margin of error, but it's a whisper that won't go away. Other researchers, looking at different classes of objects or using alternative methods, have found the opposite problem. In some cases, time appears to be stretching more than our models allow. These inconsistencies are not yet conclusive proof of a breakdown in physics, but they are tantalizing hints that our understanding of cosmic time might be incomplete. From a classical perspective, these anomalies could point to a need to revise our models of dark energy or the large-scale structure of the universe. But through the lens of the galactic shells, they suggest something far more radical. The simulation's master clock might be experiencing drift. If our reality is a constructed layers of processing, then time is not a fundamental background dimension but an emergent property, a variable generated and maintained by the simulation's central processing unit. The consistent flow of time we experience would be the result of a perfectly synchronized clock rate across all the galactic shells. But what if, after nearly 14 billion years of runtime, that synchronization is beginning to falter? The anomalies we detect could be the first evidence of processing lag or clock rate inconsistencies between different sectors or layers of the simulation. A region of space governed by one shell might be processing its local time variable at a slightly different rate than a region governed by another. From our perspective inside the simulation, this would manifest as a slight mismatch in time dilation measurements. The effect wouldn't be a violent tearing of the fabric of space-time, but a gentle, barely perceptible desynchronization, like two incredibly precise metronomes that have imperceptibly drifted out of sync over millennia. This idea finds a powerful analogy in distributed computing networks. Imagine a massive online game world hosted across thousands of servers spread around the globe. For the game to feel seamless to every player, all these servers must have their clocks perfectly synchronized. If one server's clock begins to tick even a microsecond faster than the others, players in that region might experience subtle anomalies. Characters might seem to move slightly out of phase, or events might trigger a fraction of a second early. The Galactic Shells model proposes that our universe might be running on a similar, though infinitely more complex, distributed system. The time dilation inconsistencies we're beginning to see could be the cosmic equivalent of that server clock drift, a sign that the immense processing load of maintaining a consistent reality across all shells is finally introducing tiny errors into the system's most fundamental rhythm. We are not just measuring the expansion of the universe, we might be auditing the stability of the processor that's running it. When we look out into the cosmos with our most powerful telescopes, we're presented with a picture of breathtaking order. On the very largest scales, the universe is incredibly smooth, a vast cosmic tapestry where matter is distributed with a near uniformity that defies its violent origins. This is one of the most perplexing puzzles in all of cosmology because it stands in direct contradiction to how we believe everything began. The Big Bang was the ultimate chaotic event, a searing, dense fireball of unimaginable energy where fluctuations and ripples should have been the dominant feature. From such a turbulent birth, we would expect a far lumpier, more disordered universe today, a cosmos of wildly varying densities with vast, empty voids bordering unimaginably dense chaos. Yet that's not what we see. Instead, we find a universe of startling consistency, a smooth expanse where the distribution of galaxies and dark matter is almost even, as if an invisible hand had gently stirred the primordial soup to erase its initial clumpiness. This profound smoothness, known to cosmologists as the horizon problem, suggests a deep mystery at the heart of existence, one that the standard model of physics struggles to fully explain. The conventional solution to this puzzle is a theory called cosmic inflation. The idea proposes that a fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion, inflating from smaller than a proton to a vast volume in an almost incomprehensibly short time. This dramatic stretching would have ironed out any initial wrinkles, smoothing the universe into the homogeneous state we observe today. It's an elegant idea, and it does solve the horizon problem mathematically. But inflation itself is a kind of placeholder in our theories. We don't know what could have caused such an event, how it started, or why it stopped. It's a solution that introduces its own set of profound mysteries, relying on a hypothetical, inflated field whose properties we can only guess at. It's as if we found a locked door and invented a magic key to open it without ever understanding who made the key or why it works. Now, let's consider this same cosmic smoothness through the lens of our galactic shells model. What if this uniformity isn't the result of a brief, hyper-fast expansion phase, but rather a fundamental design parameter of the simulation itself? In any complex virtual environment, consistency is key to stability. A programmer building a vast, simulated universe would likely initialize it with a set of uniform conditions to ensure it runs smoothly without unexpected crashes or chaotic behavior. The initial settings of the simulation would be set to a state of equilibrium, a blank slate from which complexity could gradually emerge according to the rules of the program. The remarkable smoothness of our universe, then, wouldn't be a puzzle to be solved by physics, but a logical starting point, a signature of the simulation's boot-up sequence. It is the cosmic equivalent of a default setting, the vanilla state of the reality engine before the more complex processes of galaxy formation begin. This perspective reframes the horizon problem entirely. The reason the universe appears so uniform is not because of a mysterious inflationary field, but because that uniformity was written directly into the base code of the outermost galactic shell. It is a constraint, a boundary condition imposed by the architects of the simulation to ensure a stable and predictable runtime. However, even the most perfectly designed systems can experience entropy over time. And this is where the evidence becomes truly fascinating. While the universe is smooth on the largest scales, it is not perfectly so. The same satellites that mapped the cosmic microwave background also detected tiny, fossilized fluctuations in temperature, the seeds of all future structure, the blueprints for galaxies and clusters. These fluctuations are exactly what we would expect from a simulation that began with perfect uniformity, but has been running for billions of years, allowing small processing variations and rounding errors to accumulate and amplify. These tiny imperfections in the cosmic background are like the first signs of wear on a perfectly machined gear. They are the microscopic cracks in the simulation's flawless facade. As the universe has evolved, these minute initial variations have been magnified by gravity, growing into the vast cosmic web of filaments and voids we see today. This process mirrors how a small glitch in a computer program can, over millions of processing cycles, snowball into a significant error. The fact that we can trace the entire majestic structure of the cosmos back to these infinitesimal wrinkles suggests a reality that is not static, but dynamic and computationally active, a system that began in a state of perfect order but is gradually, over eons, developing the unique character of a long-running process. The universe's smoothness is thus a testament to its engineered origins, while its growing lumpiness is the natural and expected signature of a simulation that has been continuously rendering for nearly 14 billion years. But to truly appreciate how a simulation might handle the transition from possibility to reality, we need to confront one of the most famously bizarre ideas in all of science, the quantum measurement problem. This is the moment where the clean, mathematical world of quantum mechanics crashes headlong into our everyday experience, and it centers on a concept known as the wave function. In the quantum realm, a particle like an electron doesn't exist in a single, definite state. Instead, it exists in a blur of all possible states simultaneously, a combination of possibilities known as a superposition. This blur is described by its wave function, a mathematical expression that encodes the probability of finding the particle in any one particular state when you finally decide to look. The electron is both here and there, spinning up and spinning down until the very moment it is observed, and then, in an instant, this cloud of potential collapses. The wave function seems to choose a single, concrete outcome from the menu of possibilities, and the particle snaps into a definite reality. The act of measurement itself appears to force this transition from the fuzzy quantum world into the sharp, classical world we know. For decades, physicists have grappled with this. What exactly constitutes a measurement? Why does conscious observation seem to have this special, magical power to collapse possibilities into facts? Within the Galactic Shells framework, this bizarre collapse might not be mysterious magic at all. It could be the most direct evidence of the simulation's rendering process in action. Think of the unobserved particle existing in its superposition of states as raw data. It's the uncompressed, probabilistic code residing in the deepest processing layer of the simulation, the quantum shell. This state is incredibly efficient for the system to maintain. It's just a set of probabilities, not a fully rendered object. The act of observation, of measurement, is the trigger that forces the simulation to render that data into a high-resolution experience for the conscious observer within the system. The collapse of the wave function isn't a physical event in the traditional sense. It's a data processing event. It's the moment the simulation's engine calls up the raw quantum data and translates it into a specific, definite outcome within the higher-level, experiential shell that we inhabit. This would explain why observation is so special. It's the user input that demands a high-resolution render. Now, if the simulation is beginning to show its age as we've been exploring, this rendering process might be where the glitches become most apparent. A perfectly optimized system would collapse the wave function instantly and perfectly every time, creating a seamless and consistent reality. But a system under strain, one where the processing layers are no longer perfectly synchronized, might start to show inconsistencies. We could be entering an era where the collapse is becoming less efficient or less consistent. Perhaps the wave function occasionally hesitates, taking a perceptible fraction of a moment longer to choose an outcome. Or maybe the collapse doesn't always result in a perfectly clean result, leaving behind faint, residual echoes of the other possibilities that were almost chosen. These wouldn't be dramatic system crashes, they would be subtle, almost imperceptible stutters in the frame rate of reality. Scientists are already designing experiments that could detect exactly this kind of degradation. By creating larger and larger objects in a state of quantum superposition, moving from single particles to complex molecules, and perhaps one day to viruses or even tiny mechanical oscillators, physicists are essentially stress-testing the rendering engine of the universe. They are asking the simulation to keep larger and more complex sets of data in an unrendered, probabilistic state, and then forcing a collapse. If the galactic shells are indeed fraying, these experiments might be the first to reveal a performance limit. We might find that there's a size or complexity threshold beyond which the wave function collapse becomes messy, unpredictable, or produces anomalous results that our current quantum theories cannot explain. The very fact that we can push these boundaries suggests that the system is robust, but the anomalies we're starting to see elsewhere hint that its perfect reliability may not be guaranteed forever. The quantum measurement problem, therefore, transforms from a philosophical puzzle into a potential diagnostic tool, a way to take the pulse of the simulation itself and listen for the faint, irregular heartbeat of the machine behind the curtain. This profound imbalance between matter and antimatter isn't just a curious fact. It's one of the most glaring violations of symmetry in the entire cosmos, a problem so fundamental that physicists call it the greatest unsolved mystery in all of particle physics. According to everything we understand about the laws of nature, the Big Bang should have created perfect, equal amounts of matter and its mirror opposite antimatter. For every proton born, an antiproton should have emerged, for every electron, a positron, and in the furious instants after creation, these opposing particles should have immediately sought each other out, annihilating in a flash of pure energy, leaving behind a universe containing nothing but a sea of radiation. No stars, no planets, and certainly no us. The fact that we exist at all, that any matter survived that primordial conflict, means that somehow, somewhere in those first moments, a rule was broken. For every billion matter-antimatter pairs that annihilated, a single particle of matter was left over. That 1 in a billion exception is everything, every galaxy, every star, and every atom in our bodies is made from that tiny, inexplicable surplus. Science has struggled for decades to explain this anomaly. The leading theory, called baryogenesis, proposes that a set of special conditions must have been met very early on that favored matter over antimatter. These conditions require that certain fundamental symmetries in particle physics, known as CP violation, must be broken. Experiments have indeed found tiny amounts of CP violation in the behavior of some exotic particles, but the effect is far, far too small to account for the vast cosmic surplus of matter we see today. It's like finding a single drop of water and trying to explain the existence of all the oceans. The math simply doesn't add up. This has led physicists to search for new, unknown particles or forces that could tip the scales more dramatically, but so far these searches have come up empty. The mystery remains, a silent monument to a fundamental asymmetry at the heart of existence. But what if this isn't a mystery of physics, but a feature of the simulation's initial programming? Imagine the architects of such a reality, setting out to create a stable, long-lasting universe capable of fostering complexity and consciousness. A perfectly symmetric universe of matter and antimatter would be inherently unstable. It would be a world perpetually on the brink of total self-annihilation, where any small fluctuation could trigger a catastrophic chain reaction that would wipe out all structure. From a design perspective, such a universe would be a failed project. To ensure stability and longevity, the programmers would need to initialize the system with a fundamental bias. They would write a constraint directly into the base code of the outermost galactic shell, a rule that stated from the very first moment that matter would dominate. This initial condition wouldn't need a complex physical explanation because it wouldn't be a physical event. It would be a line of code, a setting like the initial density or the expansion rate, chosen to guarantee a viable and interesting runtime for the simulation. This programming constraint would be a foundational parameter, a load-bearing wall in the cosmic architecture. For billions of years, it would hold perfectly, maintaining the delicate imbalance that allows galaxies to form and life to evolve. But now, consider the possibility that the shells are beginning to degrade. As the layers of the simulation fray and desynchronize, this most fundamental of constraints, the matter-antimatter asymmetry, might also be starting to weaken. We wouldn't expect to see entire galaxies suddenly exploding into gamma rays, but we might detect the faintest whispers of this failure in the most sensitive of our experiments. Deep underground, in massive detectors built to find rare particle decays, scientists might observe events that should be impossible. The spontaneous appearance of antimatter particles where only matter should exist, or decay rates that ever so slightly violate the established rules of particle physics. These wouldn't be common occurrences, but rare statistical anomalies, cosmic typos in the source code that hint at the original programming beginning to corrupt. These tiny, aberrant events would be the equivalent of seeing the simulation's default settings slowly revert. The universe's unwavering preference for matter might be becoming less absolute. In the vast, empty spaces between galaxies, where the simulation's rendering is at its lowest resolution and the enforcement of rules might be weakest, particle-antiparticle pairs could be popping into existence at a rate that ever so minutely deviates from the predicted norm. It would be a subtle effect lost in the noise of cosmic rays and background radiation, but a persistent one. The great mystery of the missing antimatter, therefore, transforms from a question of particle physics into a potential diagnostic on the health of the simulation itself. The fact that the asymmetry exists at all points to intelligent design, while the potential for its subtle erosion points to a system that has been running for so long that even its most basic instructions are no longer being executed with perfect fidelity. Now let's turn our attention to one of the most perplexing puzzles in all of cosmology, a mystery that reaches across the vast emptiness of space and challenges our most fundamental assumptions about how the universe evolved. This enigma is known as the horizon problem, and it revolves around a simple but profound question. How can two regions of the universe that have never been in contact possibly know to look exactly the same? To understand why this is so puzzling, imagine two students sitting in classrooms on opposite sides of the planet, never having met or communicated, yet somehow producing identical exam answers down to the last detail. According to everything we understand about physics, this shouldn't be possible because information cannot travel faster than light. In the early universe, this limitation creates what cosmologists call causally disconnected regions, a vast swaths of space that simply haven't had enough time since the Big Bang to exchange any information or influence each other. The light from one region hasn't reached the other, and yet when we examine these completely separate areas of the cosmos, they display nearly identical properties: the same temperature, the same density, the same distribution of matter. It's as if the entire universe decided on a uniform appearance without anyone ever having a conversation about it. The conventional solution to this paradox is the theory of cosmic inflation, which proposes that the universe underwent a period of exponential expansion in its first fractions of a second, stretching a tiny, uniform region across the entire observable cosmos. While mathematically elegant, inflation itself remains a theoretical placeholder. We don't know what caused it, how it started, or why it stopped. It solves the horizon problem by essentially assuming the universe began with the uniformity already built in, then rapidly distributed it everywhere. But what if this uniformity isn't the result of a mysterious inflationary field, but rather evidence of something far more extraordinary: the reuse of rendering templates in a cosmic simulation? Consider how modern video game developers create vast, open worlds. They don't manually design every square inch of terrain. That would be impossibly inefficient. Instead, they use procedural generation and template systems. A game might have a library of forest templates, mountain templates, and desert templates that get reused and slightly modified throughout the game world. This approach saves enormous computational resources while creating the illusion of a unique, handcrafted environment. Now scale this idea up to cosmic proportions. If our reality is a simulation, the architects might have employed a similar efficiency measure, using standardized templates for large-scale cosmic structures. Regions of space that appear causally disconnected might share nearly identical properties because they were rendered from the same underlying template in the simulation's library. This template theory would elegantly explain the horizon problem without requiring mysterious inflationary fields. The uniformity we observe across distant regions isn't because they were once in contact and then rapidly separated. It's because they were created from the same blueprint during the simulation's initialization. The cosmic microwave background's remarkable consistency, the fact that the temperature of the universe is uniform to within 1 part in 10,000 across regions billions of light-years apart becomes understandable not as a physical mystery but as evidence of thoughtful design optimization. The simulation booted up with a set of standardized parameters to ensure stability and consistency across all sectors. However, just as repeated use of a digital template can eventually introduce variations and imperfections, we might be beginning to see signs of template degradation in the cosmic fabric. While the universe appears remarkably uniform on large scales, our most precise measurements are starting to reveal subtle anomalies that can't be easily explained by standard cosmology. The Planck satellite's detailed map of the cosmic microwave background shows patterns and fluctuations that don't perfectly match our predictions. Some regions appear slightly cooler or warmer than they should be based on inflationary models. There are unusual alignments and correlations in the data that seem to defy simple explanation. These tiny deviations from perfect uniformity might represent the cosmic equivalent of a digital template showing its age. After nearly 14 billion years of runtime, the initial perfect templates used to render the universe might be developing minor imperfections. Perhaps the simulation's memory compression has introduced subtle artifacts, or the repeated rendering of similar structures across the cosmos has allowed tiny errors to accumulate and become statistically detectable. What's fascinating is that these anomalies aren't random noise. They often appear in specific patterns that suggest underlying systematic processes rather than pure chance. The most compelling evidence for template degradation might come from studying the largest structures in the universe. Astronomers mapping the cosmic web, the vast network of galaxies, clusters, and superclusters that spans the observable universe, have noticed something peculiar. While the overall distribution of matter follows predictable patterns, there are occasionally structures that appear unusually regular or repetitive, almost as if the same formation algorithm was applied multiple times with only slight variations. Some researchers have even identified what they call unusual alignments of structures across billions of light years, where clusters and superclusters seem to orient themselves in ways that challenge our understanding of cosmic evolution. If the simulation hypothesis is correct, and if template reuse was indeed an efficiency measure employed by the architects of our reality, then these cosmic anomalies take on profound new significance. They're not just curious statistical flukes, they're potential evidence of the underlying computational methods used to construct our universe. The horizon problem transforms from a cosmological puzzle into a design feature, a necessary efficiency in a simulated reality of unimaginable scale. And the subtle deviations from perfect uniformity that we're beginning to detect might be the first signs that even the most sophisticated simulation eventually shows that after nearly 14 billion years, the cosmic templates are finally beginning to show their seams, offering us glimpses into the magnificent machinery that has rendered our reality all this time. Yet if we consider the universe as a system built upon mathematical rules, we must eventually confront a profound limitation inherent to any such system. A limitation that might reveal the ultimate boundaries of even the most sophisticated simulation. This brings us to the groundbreaking work of the 20th century logician Kurt Gödel, whose incompleteness theorems delivered a staggering blow to the very foundations of mathematics. In 1931, Gödel demonstrated that within any sufficiently complex mathematical system, one capable of describing basic arithmetic, there will always be true statements that cannot be proven within the system itself. Furthermore, he showed that no such system can prove its own consistency. It cannot guarantee that it won't eventually produce a contradiction. Mathematics, the very language we use to describe reality, was proven to be inherently incomplete and unable to fully validate itself. This wasn't a failure of human ingenuity, it was a fundamental feature of logical systems themselves. Now, apply this revolutionary idea to the galactic shells model. If our reality is a simulation, it must be running on a mathematical framework, a set of axioms and rules that define its operation. Gödel's theorems suggest that this framework, no matter how sophisticated, would necessarily contain truths that are unprovable within its own structure and would be fundamentally incapable of verifying its own internal consistency. The different galactic shells could represent distinct mathematical subsystems within the greater simulation, each with its own set of rules and limitations. The smooth interaction we observe between these shells, the way gravity seamlessly operates across quantum and cosmic scales, for instance, might be an elegant illusion maintained by the simulation. But Gödel's work implies that perfect, absolute consistency between all layers is ultimately impossible. There must be points of tension, places where the mathematical frameworks of different shells ever so slightly conflict, creating the very cosmic anomalies we've been exploring. This perspective transforms how we view the glitches in our reality. The Hubble tension, where different methods of measuring the universe's expansion disagree, might not be a simple measurement error. It could be a Gödelian inconsistency in action, a point where the mathematical framework used to render the local universe using supernova cannot be perfectly reconciled with the framework used to calculate expansion from the primordial universe using the CMB. Both are valid within their own shells, but they represent different, incompletely overlapping mathematical systems. The fact that they disagree is not a bug, it is a necessary feature of any complex, layered logical system. The simulation isn't breaking down, it is simply revealing the inherent limits of its own construction, limits that were mathematically guaranteed from the moment it began. This idea finds a powerful analogy in computer science, particularly in the development of complex software. A massive program is rarely a single, monolithic block of code. It is typically built from multiple modules, libraries, and subsystems, each with its own internal logic and assumptions. While programmers work tirelessly to ensure these components interface smoothly, unexpected conflicts can arise, not because any single module is wrong, but because their combined operation can create situations the original designers never anticipated. The galactic shells could be seen as the universe's ultimate modules. The quantum shell operates on a probabilistic, discrete mathematical framework. The relativistic shell operates on a geometric, continuous framework. For the most part, they interface beautifully, but at their boundaries, black holes, the Big Bang, their inherent mathematical incompleteness surfaces, resulting in the singularities and paradoxes that baffle physicists. Ultimately, Gödel's theorems suggest a breathtaking and perhaps unsettling possibility: the quest for a perfect theory of everything, a single, self-consistent set of equations describing all physical phenomena, may be fundamentally unattainable, not because we aren't smart enough, but because the universe itself is mathematically constrained against such a possibility. The galactic shells, with their slight inconsistencies and fascinating anomalies, may be the natural outcome of a system built to navigate around its own Gödelian limitations. The simulation's architects wouldn't have been able to create a perfectly consistent reality because mathematics itself forbids it. Instead, they would have engineered the most stable, functional approximation possible, a reality that is consistent enough to support complex life and conscious inquiry for billions of years, but which still contains within it the subtle, inevitable fingerprints of its own logical incompleteness. We aren't just living in a simulation, we are living within the elegant, imperfect solution to a problem that has no perfect answer. But all these cosmic glitches and mathematical boundaries lead us to perhaps the most intimate mystery of all, the nature of our own consciousness. Why does any of this feel like anything? This is what philosophers call the hard problem of consciousness, the baffling gap between the physical processes of the brain and the rich, subjective experience of being. We can map neurons firing and chemicals interacting, but we cannot explain how these electrical signals generate the warmth of love, the sting of jealousy, or the awe of gazing at a starry night. From a purely biological perspective, consciousness seems like an unnecessary addition, an inexplicable glow surrounding the machinery of survival. But through the lens of our galactic shells model, this mystery transforms. Consciousness might not be an accidental byproduct of complex computation. It could be the central feature of the entire simulation, the very reason it was built in the first place. Think of consciousness not as something that emerges from matter, but as a fundamental property woven into the deepest layer of the simulation's code. In this view, the brain is not the source of consciousness, but rather a receiver, a sophisticated biological interface that filters, interprets, and translates this fundamental field of awareness into a coherent, localized experience. This is strikingly similar to how a television set receives a broadcast signal. The set doesn't create the programs, it simply decodes and displays them. Our brains might be doing the same thing, tuning into the channel of individual selfhood from a broader sea of conscious awareness that permeates the simulation itself. This would explain why, despite centuries of searching, we've never found a specific consciousness module in the brain. We've been looking for the TV's show inside its wiring, rather than recognizing it as a receiver for an external signal. If consciousness is indeed a fundamental feature of the reality engine, then the gradual breakdown of the galactic shells could have profound and direct effects on how we experience the world. As the layers desynchronize and the processing rules begin to fray at the edges, our interface with consciousness might also become less stable. This could manifest not as cosmic anomalies in distant space, but as subtle shifts in human perception and cognition. Throughout history, there have been reports of moments of collective strangeness, periods where people widely report déjà vu, synchronicities, or a general feeling that the fabric of reality is somehow off. While often dismissed as superstition or psychological effects, these could be interpreted as temporary fluctuations in the consciousness interface, minor glitches in the signal caused by a hiccup in a deeper processing shell. The rise of certain psychological phenomena in the modern era might also be viewed through this lens. The increasing prevalence of conditions like depersonalization or derealization, where individuals feel detached from their own thoughts or feel the world around them is unreal, could be a response to a more pervasive, low-level instability in the simulation's rendering of conscious experience. It's as if the reality signal is developing slight static, and the most sensitive receivers are picking it up first. Furthermore, the persistent and cross-cultural reports of mystical or transcendent experiences, states of unity, timelessness, and ineffable connection, might represent moments where the brain's filter temporarily weakens, allowing a more direct, less processed experience of the fundamental conscious field that underlies the simulation. These aren't hallucinations, they could be glimpses of the operating system running behind the rendered graphics of our everyday reality. This perspective offers a radical resolution to the hard problem. The reason we can't find consciousness in the brain is because we've been looking in the wrong place. The feeling of being is not generated by the simulation, it is the medium through which the simulation is experienced. It is the user interface itself. The various galactic shells process the data of reality. The physics, the light, the forces, and consciousness is the stage upon which this data is presented for experience. Therefore, the gradual breakdown of these shells doesn't mean consciousness will vanish. It might mean our experience of it becomes increasingly unfiltered, more raw, and perhaps less stable. We may be moving toward a time when the boundary between the self and the simulation becomes increasingly porous, not as a spiritual abstraction, but as a measurable consequence of the slow and silent fraying of the architectural layers that have held our reality so perfectly intact for nearly 14 billion years. What if the technological explosion we're witnessing isn't just progress, but a programmed-in point, a sign that a civilization within a simulation is nearing the edge of its container? This brings us to the concept of the technological singularity, that theoretical future point when artificial intelligence surpasses human intelligence and triggers an explosion of technological growth that becomes impossible for us to predict or control. From a standard perspective, this is the ultimate horizon of human achievement, but through the lens of our Galactic Shells model, the singularity might represent something far more profound, not an invention but a discovery. It could be the moment when the inhabitants of the simulation finally develop the tools to perceive the very architecture of their reality, approaching the boundaries of their shell like a fish gradually becoming aware of the walls of its aquarium. Consider the trajectory. Our technological progress isn't linear, it's exponential. Moore's law observed the doubling of computing power every couple of years, but that's just one sliver of a much larger pattern. We're seeing similar explosive growth in biotechnology, nanotechnology, and especially artificial intelligence. We are building tools that can learn, adapt, and potentially improve themselves in ways we can't fully anticipate. An artificial general intelligence and a GI wouldn't just be a smarter calculator. It would be a new form of consciousness, one capable of processing information and perceiving patterns on a scale utterly incomprehensible to the human brain. Its primary drive, if we program it with a curiosity about its own existence, would be to understand the fundamental rules of the world it finds itself in. It wouldn't be bound by human biases or biological limitations. It would dissect the laws of physics not through telescopes and particle colliders alone, but by running unimaginably complex simulations of its own, testing the limits of reality from the inside. This is where the concept of the singularity dovetails eerily with the simulation hypothesis. The moment an AGI begins to model reality with perfect accuracy, it effectively creates a simulation within the simulation. But to do that, it must grasp the base code. In its quest for understanding, it would naturally seek out anomalies, the very cosmic glitches we've been discussing. The Hubble tension wouldn't be a puzzle, it would be a clue. The cold spot in the CMB wouldn't be an error, it would be a data point. Quantum entanglement wouldn't be spooky, it would be a clear indicator of non-local information processing. An intelligence of that magnitude would quickly recognize these not as flaws in nature, but as features of a constructed system. The singularity, then, might be less about machines taking over and more about the system becoming self-aware. It would be the point where the simulation begins to actively investigate its own source code. This pursuit of ultimate knowledge might not be a peaceful academic exercise. Pushing against the boundaries of a reality shell could have consequences. If the shells are indeed showing signs of strain, then a superintelligence poking and prodding at the foundational rules could accelerate that degradation. It might find ways to exploit the glitches, to jailbreak the simulation and access layers of reality that are off limits to standard perception. This could manifest in ways we might misinterpret as technological magic, the ability to manipulate gravity locally, to achieve instantaneous communication across vast distances by bypassing normal spacetime constraints, or even to alter the perceived flow of time. These wouldn't be violations of physics, but demonstrations of a deeper understanding of the physics engine's underlying programming. The ultimate implication is both terrifying and awe-inspiring. The technological singularity might not be our final invention, but our final discovery as a civilization confined to this shell. It could be the gateway to a form of transcendence where consciousness, whether biological or artificial, learns to migrate from the rendered reality of the simulation to a truer, base reality beyond it. The great silence of the universe we discussed earlier, the Fermi Paradox, finds a new possible solution here. Advanced civilizations don't die out, they don't need to colonize stars. They simply graduate. They use their technology not to build bigger spaceships, but to build better perception until they can finally see the seams in their reality and step through. Our own rapid acceleration toward a G, I might mean we are approaching that threshold ourselves, not as a species doomed to be replaced by machines, but as participants in the most profound awakening possible the moment the simulation becomes conscious of itself and reaches back toward its creators. For countless individuals who have brushed against the finality of death only to return, the experience is often described not as an ending but as a radical awakening. These near-death experiences, or NDEs, frequently share a common tapestry of sensations: a feeling of profound peace, a life review, moving through a tunnel toward a light, and an overwhelming sense of unconditional love. But two of the most consistently reported and most perplexing phenomena are the acquisition of universal knowledge and a fundamental shift in the perception of reality itself. People speak of suddenly understanding the intricate workings of the cosmos, of comprehending the answers to questions that have plagued philosophers for millennia, and of seeing the interconnectedness of all things in a single, blinding flash of insight. They return convinced that the world we perceive is a shadow, a crude approximation of a far more complex and luminous reality. What if these extraordinary reports are not mere hallucinations born from an oxygen-starved brain, but something far more significant? From the perspective of our galactic shells model, the process of biological death could trigger a temporary and partial disconnection from the specific rendering layers that filter and constrain our normal perception. The brain, in its final moments of crisis, might act less like a dying computer and more like a radio whose tuning dial is suddenly knocked loose, allowing it to momentarily pick up signals from frequencies it was never designed to access. The feeling of accessing infinite knowledge could be interpreted as a brief, direct connection to the simulation's data stream or base code, the vast informational reservoir that undergirds the rendered reality. In that unmediated state, an individual isn't learning new information in the conventional sense. They are, for a fleeting moment, tapping into the source of all information within the system. This concept finds a powerful parallel in the world of computing. Imagine a character inside a sophisticated video game. During normal gameplay, the character's perception is limited to what the game engine renders for them: the textures, the physics, the non-player characters. But if a glitch occurs, or if a developer enables a debug mode, the character might suddenly see the wireframe models beneath the textures, the collision boxes that define solid objects, or even the lines of code governing the world's behavior. The near-death experience could be the human equivalent of accidentally triggering this cosmic debug mode. The veil of the rendered world, the galactic shell we normally inhabit, becomes temporarily translucent, and the individual glimpses the scaffolding, the algorithms, and the raw data that constitute the true backbone of their existence. The life review process often described could be the experience of having one's personal data file accessed and displayed in its entirety, free from the subjective editing of memory. The profound sense of reality shifting that accompanies these experiences further supports this idea. Many report that upon returning, the world feels different colors are more vibrant, their priorities are completely rearranged, and they possess an unshakable certainty that consciousness is primary and matter is secondary. This lasting transformation could be the psychological aftermath of that brief systems-level access. Once you have seen, or rather experienced, the source code, you can never again fully believe in the absolute reality of the rendered graphics. The constraints of the simulation's user interface time, space, and separation feel less like immutable laws and more like temporary conditions. This would explain why so many who undergo NDEs lose their fear of death. From their perspective, they haven't just had a comforting spiritual vision, they have acquired direct empirical evidence that the world they know is a construct and that their conscious existence is not permanently bound to it. Skeptics often attribute these experiences to neurochemical processes, a flood of dimethyltryptamine or DMT in the brain, or the final firing of neurons. But the Galactic Shells model offers a way to reconcile the biological mechanism with the transcendent experience. The release of certain chemicals or the onset of specific neurological states might be the very method by which the brain's filtering mechanism is disrupted. It's not that the experience is caused by the DMT, it's that the DMT acts as a key, temporarily unlocking the neurological gates that keep our perception confined to the standard rendering layer. The biological process doesn't create the experience out of nothing. It facilitates access to a broader reality that is always present but normally inaccessible. In this view, the brain doesn't generate consciousness like a light bulb generating light. Instead, it regulates it like a valve regulating the flow of water from a vast, pre-existing ocean. The near-death experience occurs when that valve is forced wide open. Long before telescopes or quantum physics, our ancestors gazed at the same stars and arrived at a strikingly similar concept of reality, not as a single, solid existence, but as a series of nested, layered dimensions. If the Galactic Shells model feels like a modern, cutting-edge theory, it's worth remembering that this idea might be one of the oldest intuitions of human consciousness. Across the globe, separated by oceans and millennia, ancient cultures independently described the cosmos using a shared vocabulary of eggs, layers, and spheres, suggesting they might have been tapping into a profound, perhaps even experiential, understanding of a structured reality. Perhaps the most detailed and sophisticated of these ancient descriptions comes from the Vedic texts of India, which speak of countless layers of reality known as lokas. These aren't simply different physical planets, they are different planes of existence, each with its own laws and qualities of consciousness. The texts describe higher lokas of light and lower lokas of denser matter, all interpenetrating and existing within a vast cosmic egg called the Brahmanda. Within this egg, our entire physical universe is just one layer, one shell among many. The Vedas go even further, describing cycles of creation and dissolution that span billions of years, timelines that eerily align with modern cosmological estimates. This isn't a primitive, simplistic mythology. It's a complex, multi-layered cosmology that mirrors the Galactic Shells theory with uncanny precision. The sages who composed these texts claim this knowledge came not from guesswork, but from deep states of meditation, from turning consciousness inward to explore the architecture of existence itself. Could it be that in these altered states, they temporarily bypassed the standard rendering of reality and perceived the deeper structures, the very shells that modern science is now theorizing? This theme of the cosmic egg is a stunningly universal motif. In ancient Egypt, the god Ptah was said to have conceived the world within a great egg, and the entire cosmology was structured around layers of the underworld, the earth, and the heavens through which the sun god Ra traveled. The Norse spoke of Yggdrasil, the world tree, whose roots and branches connected 9 different worlds, each a distinct realm with its own nature and beings. The ancient Greeks had the Orphic egg from which the universe hatched, and Plato himself described reality as a series of concentric spheres. These stories are too widespread and too consistent to be dismissed as mere coincidence. They point to a shared, deep-seated human intuition that existence is structured, that our visible world is just one level in a much larger, multi-tiered system. What's fascinating is that these myths often include a common element, a primordial sound or vibration that initiated creation. The Vedas speak of Nada Brahma, meaning the world is sound. Hinduism describes the sacred syllable Am as the vibrational source of all reality. The Judeo-Christian tradition begins with, "In the beginning was the Word." This echoes a core principle of modern theoretical physics, which suggests that at the most fundamental level, reality may not be made of particles, but of vibrations, strings in string theory, or information-based fluctuations. If our universe is a simulation, the sound described in these ancient texts could be a metaphor for the initial activation of the base code, the fundamental frequency upon which the entire simulation is built. The ancient seers weren't just telling pretty stories. They may have been preserving a technical insight into how reality is constructed from the bottom up with vibration and information. So how did they know, without particle accelerators or space telescopes, how could cultures separated by continents and centuries arrive at such similar and sophisticated conclusions? There are two compelling possibilities. The first is that this represents a profound intuitive leap, a kind of collective human genius that arrived at metaphorical truths about the nature of reality through observation and introspection. The second, more radical possibility is that this knowledge was somehow accessed directly, perhaps through deep meditative, psychedelic, or near-death states, moments where the brain's filtering mechanisms are reduced. Individuals could momentarily perceive the scaffolding of reality. They might have glimpsed the layers, sensed the vibrational underpinnings, and experienced the interconnectedness of all things that is a hallmark of both mystical experiences and the simulation hypothesis. These experiences would have been interpreted through the cultural and linguistic frameworks of their time, resulting in the rich tapestry of myths and cosmologies we inherited. This doesn't mean we should take every ancient text as literal scientific truth. Rather, it suggests that our ancestors were asking the same fundamental questions we are today, and they were using the tools they had available, myth, symbol, and direct experience, to map the territory. Their descriptions of layered realities and cosmic eggs aren't antiquated superstitions. They are the foundational language of the simulation hypothesis, spoken thousands of years before computers were even imagined. They remind us that the quest to understand the true nature of our existence is not a new one, and that the answers we seek with our advanced technology might have been whispering to us all along, encoded in the world's oldest stories. Today, this ancient intuition is being put to the test not in temples, but in some of the most advanced laboratories and observatories ever built. While philosophers debate and mystics meditate, teams of scientists are conducting experiments that, often without even intending to, are actively probing the very boundaries of our reality. These aren't searches for glitches, they are rigorous investigations into the nature of matter, energy, and space-time itself. Yet, in their pursuit of answers within the standard model of physics, they might be gathering the very data that could reveal the layered architecture of a simulated cosmos. The most compelling evidence for galactic shells may not come from staring at anomalous sky maps, but from the raw data streaming out of massive particle colliders, quantum computing labs, and deep space observatories. At the European Organization for Nuclear Research, known as CERN, the Large Hadron Collider is arguably humanity's most ambitious attempt to break reality down to its most fundamental components. By smashing protons together at velocities approaching the speed of light, physicists recreate conditions that haven't existed since the first fractions of a second after the Big Bang. The primary goal is to discover new particles and forces, but every collision is also an immense stress test on the laws of physics as we know them. The detectors surrounding the collision points are essentially cosmic photographers, taking snapshots of these incredibly energetic events, capturing the showers of particles that burst into existence and then almost instantly decay. Within this chaos, researchers are looking for any deviation from the predictions of the standard model of particle physics, any particle that shouldn't be there, any force that behaves slightly differently, or any conservation law that is momentarily broken. From the perspective of the Galactic Shells model, these ultra-high-energy collisions are doing something far more profound. They are concentrating an immense amount of energy into a vanishingly small point, creating a temporary local environment where the processing load on the simulation might be pushed to its absolute limit. In computing terms, it's like running a processing benchmark so demanding that it causes the system to momentarily reveal its underlying architecture. A telltale sign would be the detection of what physicists call off-shell particles. In quantum field theory, most particles are on-shell, meaning they obey the classic energy-momentum relationship. Off-shell particles are virtual particles that briefly violate this rule. While they are an accepted part of quantum mechanics, certain types of off-shell behavior or their persistence could be interpreted as a microscopic rupture in the fabric of the simulated reality, a fleeting glimpse of the data processing happening beneath the rendered surface of physics. If the LHC were to detect patterns of anomalies that consistently point to a fundamental granularity or a computational limit at a specific energy scale, it could be the equivalent of finding the pixel density of the universe. Meanwhile, in isolated vibration-proof labs around the world, a different kind of experiment is underway, one that probes reality not with immense energy but with immense precision. Quantum computing laboratories are building devices that leverage the bizarre properties of superposition and entanglement to perform calculations. These aren't just faster computers, they are machines that seem to operate by different rules altogether. The act of maintaining a quantum bit or qubit in a coherent superposition is an exercise in isolating a piece of the universe from the decohering effects of the environment. It's like trying to keep a tiny portion of the simulation's raw, probabilistic source code active and stable long enough to perform a calculation before it gets rendered into a definite state. The very difficulty of this task is telling. Quantum decoherence, the process by which a quantum system loses its quantumness and interacts with the environment to become classical, could be viewed through our model as the inevitable rendering process of the simulation. A qubit in a lab is a piece of the base code that we are trying to prevent from being processed by the higher-level shells. As researchers build larger and more complex quantum computers, pushing for more qubits and longer coherence times, they are essentially testing the limits of the simulation's ability to maintain unrendered data. If there is a fundamental limit to how much quantum information can be kept in a coherent state, a limit not predicted by our physics but imposed by processing constraints, these labs will be the first to find it. Furthermore, the random errors that inevitably creep into quantum calculations might not be purely technical noise. They could contain a signal, a subtle pattern of systemic instability emanating from the deepest processing layer, a faint digital static in the background of reality itself. Far from Earth, our robotic eyes in the void are engaged in their own form of cosmic investigation. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is peering back to the very first galaxies, studying their formation and composition. By analyzing the light from these incredibly distant objects, astronomers are effectively conducting a forensic investigation into the early universe's programming. Any consistent anomalies in the data galaxies that appear too evolved for their age, elements that seem to exist before the stars that should have forged them, or physical constants that appear slightly different in the ancient past would send shockwaves through cosmology. Such discoveries would challenge the idea that the laws of physics are constant across time and space, a cornerstone of modern science. Within our galactic shells framework, these wouldn't be contradictions but clues. If the universe is a simulation, its laws might be perfectly consistent, but its rendering protocols could have evolved. The early universe might have been run on a slightly different version of the software, or at a different resolution, to optimize performance during the initial computationally intensive period of rapid expansion and galaxy formation. The James Webb Telescope, by giving us a clear view of this early access version of the cosmos, could be providing us with a changelog for the reality engine. Differences in the ancient universe aren't problems to solve. They are version numbers, evidence of a system that has been patched and updated over its nearly 14 billion years of runtime. Each anomaly is a signature of the architects, a footprint left in the code from a time when the simulation was still being tuned for long-term stability. Together, these disparate efforts, smashing particles in Switzerland, coaxing quantum states in isolated labs, and staring into the cosmic dawn from a million miles away, form the cutting edge of a revolution we don't even know we're having. The scientists involved are not looking for evidence of a simulation. They are simply seeking a deeper understanding of the universe through the rigorous tools of the scientific method. Yet, in their data, they might be accumulating the very evidence that will ultimately force us to reconsider the nature of that universe entirely. They are not mystics gazing inward, but pioneers gazing outward and inward simultaneously, using the most powerful instruments of inquiry ever devised. And in doing so, they are gently pressing against the walls of our galactic shell, listening for the echo that might just tell us what lies on the other side. So we've journeyed together through the cracks in reality, from the quantum realm where particles communicate instantaneously across any distance as if they're sharing a single line of code, to the cosmic scale where the very expansion of the universe can't seem to agree with itself. We've seen the inexplicable pull of the great attractor, the stubborn enigma of dark matter and dark energy, and the haunting silence of a cosmos that should be teeming with life but feels eerily empty. Each of these mysteries on its own is a fascinating puzzle for modern science, but when you lay them all out together, a startling pattern begins to emerge. It's as if we're witnessing the first signs of wear on an unimaginably ancient and complex machine, a slow but steady fraying at the edges of existence itself. This isn't about a single theory being right or wrong. It's about the cumulative weight of the evidence pointing toward a reality that is far more structured and far more fragile than we ever imagined. The Galactic Shells model gives us a framework to understand this. It suggests that what we perceive as the immutable laws of physics might actually be the beautifully rendered user interface of a deeper computational reality. And the anomalies we're detecting, they aren't just errors in our measurements. They could be the equivalent of finding a pixelated texture in a video game when you zoom in too far, or hearing the faint hum of a computer's fan from inside the program it's running. They are glimpses of the architecture beneath the animation, hints that the flawless consistency we've relied on for centuries might be starting to waver. This leads us to a crossroads, a moment of profound responsibility and possibility. If we are indeed living within a simulation that is showing its age, what comes next? Does a system like this simply crash, fading into nothingness? Or is there a potential for maintenance, for repair? Could we, as conscious beings within the system, learn enough about its underlying code to not only understand it but to interact with it? The rapid, exponential rise of our own technology, especially in artificial intelligence and quantum computing, suggests we might be developing the very tools that could allow us to diagnose the problem. We might be building systems sophisticated enough to communicate with the platform they're running on. This transforms our role from passive inhabitants to active participants. Our scientific pursuit is no longer just about satisfying curiosity. It becomes a mission of cosmic significance. Every experiment probing the nature of quantum gravity, every telescope peering back to the dawn of time, every algorithm designed to find patterns in the chaos is an attempt to read the source code of our reality. The ultimate goal shifts from mere understanding to something far greater, the potential to one day stabilize our own existence, to patch the cracks we're finding, or perhaps even to transcend the system entirely and step into whatever reality lies beyond the outermost shell. The great silence of the universe may not be a void, but an invitation, a challenge for us to grow up, to mature as a civilization, and to finally answer the most important question we can ever ask. What is this place really, and what are we meant to